All right, today we're going to be talking about how to make a velocity versus time graph. So before we get too deep into this, it's probably important that we have some kind of understanding about how to read a qualitative velocity versus time graph. So qualitative basically just means there are no numbers, okay? So all we would have here is a velocity time graph, and we've got two objects on here for comparison. Notice that I always have a velocity versus time graph. There's always going to be a negative region here below the time axis. So here what I'm saying is that we're going to have the time axis, and here is the origin, which means all the numbers before that, below that point, are negative, and all the numbers above that are positive. Okay, so understanding this, the fact that this is the positive side of the velocity axis and this is the negative side of it, is a huge deal when it comes to reading these things. So right off the bat, we can tell that object A has a positive velocity. Why? Because it's above the time axis here. And meanwhile, object B has a negative velocity because it's below the time axis. Based on that and what we know about velocity, we should be able to tell that object A is moving forward and object B is moving backward. So now that we've got direction out of the way, we need to be able to figure out which direction or which object is moving faster. So the other way to notice this is to kind of put numbers or imagine numbers here on your axis. So here is 1, 2, 3, and 4. And I'm going to put numbers here below. So this is -1, -2 meters per second, -3 meters per second, and -4 meters per second. So if you take a look at what we just did, you'll notice that right off the bat, we can tell that based on the tick marks we're using to help us solve this problem, we can see that object A clearly has a velocity of +1, while object B has a velocity of -4. So object B is moving backwards, however, it's moving faster because the number 4 is greater than 1. Even though, yes, it's a negative number, it's a larger number than 1 is. So object B is moving much faster. So what we have here is this pattern that you can use. So it first depends on which half of the graph you're on. If you're on the upper positive side, we can say that the further away you get from 0, the faster you're going. Likewise, the further you get away from 0, it's the same thing, that you are going faster. So you'll notice that object B is further away from 0 than object A is. Therefore, object B is moving faster. Okay, so let's try this example. One of the goals here for this class is being able to move from one graph to the other and make sure that all graphs are telling the same story. So here we've got a position versus time graph, and we can tell that the object starts at 20 meters and is moving forward with a velocity of +5 meters per second. Okay, so the first thing that we need to be able to do is first let's figure out how fast it's traveling at a few different points. So I'm going to ask for 3 points here, 1 second, 2 seconds, and 3 seconds. Let's ask ourselves, okay, how fast is it moving at 1 second? Now, if you take a look at this line, you'll notice that at this point of this line, the slope of the graph is 5. So therefore, at 1 second, we're going to graph 5 meters per second here for a velocity versus time graph. We're going to do the same thing for 2 seconds. So at 2 seconds, let's ask ourselves, okay, well, what is the slope of the graph at this point in the line? And we look at the graph and you say, oh, it's still 5 meters per second. So what we're going to do is at 2 seconds, we're going to graph 5 meters per second. And then we're going to do the same thing for 3. And we will notice, and this time we won't be so surprised, but this time it's 5 meters per second. So when we connect these dots, you'll see that this gives us a horizontal line. And notice that the velocity is constant. So the velocity is unchanging. It's always positive 5 meters per second. So that's how you would go from position time graph to a velocity time graph. One thing we'll go to later is I want you to notice that nowhere in the velocity time graph does this 20 meters show up. This 20 meters does not show up. Okay, so we'll talk more about that towards the end of the video. So here we can do this a little bit more sped up. We'll take another 3 points, and let's say this is 1 second again, 2 seconds, and then 3 seconds, and we'll notice that if you were to check the velocities at each point on that line, they will all be -10. So what we're going to do is find 1, 2, and 3 seconds, and then make sure that we graph -10 for all 3 seconds. So I'm just going to make up a -10 here. Let's say it's there, -10 meters per second. And we've got, for 1, 2, and 3 seconds, we've got -10 meters per second. And there it is. All right, so for the second half of this video, we're going to be talking about how to go from words to a velocity versus time graph. So it's important that we be able to also go from a verbal description to a velocity versus time graph. So here's how we're going to do it. So in this story, a dog starts at rest for 5 seconds and then starts walking forward at 2 meters per second for another 5 seconds. So in this unit, we're all only dealing with constant velocities. So the constant velocities mean that our velocity time graphs will only be horizontal lines in this unit. So it looks like we need to mark off the first 5 seconds, which I'll do here. And then another 5 seconds gives us 10 seconds. Okay, so that's going to account for the first half and the second half of the story. So let's ask ourselves, okay, what is the dog doing during the first half? Well, it looks like it's just resting, which means if you're at rest, your velocity is 0. So there's your 0 velocity. And for the second half, we've got that it's moving forward at 2 meters per second. So here what we need to do is we want to find any place where you can mark 2 meters per second, and we will draw a horizontal line and make sure that it's only doing the 2 meters per second during the second half of the story. And then we're going to check, okay, let's see. The dog starts at rest for 5 seconds, so we've got a 0 velocity for 5 seconds, and it starts walking forward at 2 meters per second for another 5 seconds. So as long as your graph matches up exactly with what the words say, you shouldn't go wrong. Okay, so for this one, let's try another example. We've got a cat slowly walks left for 3 seconds, gets scared, and runs away to the right for 7 seconds. Okay, so we're going to mark off our important times. So our important times here are the first 3 seconds, which I'll draw a little bit closer to 0. So that's our first 3 seconds. And then 7 seconds later, we are going to be put at 10. Right? So you'll notice here that real quick, the first 3 seconds and then 7 seconds after that will put us at 10. So again, like the last story, this all takes place in 10 seconds. Now, let's figure out what it's doing. So a cat slowly walks left for 3 seconds, gets scared, and runs away to the right for 7 seconds. Now, in this problem, this is a qualitative problem. We're not given any velocity numbers, and that's okay. What we're going to do is know how velocity versus time graphs work and say, okay, well, if it's slow, we want to make sure that it's very close to the time axis. So what we're going to do here is we're going to draw a line that's very close to the time axis. So that's going to represent what the cat is doing for the first 3 seconds. Now you'll notice that it says left. Left typically means the negative direction. So left is usually negative and right is usually positive. So if it's running away, then we want to make sure that it runs away to the right. So we need to make sure that's fast. So faster means this. Okay, so our graph needs to be horizontal. And there we go. We've got a velocity versus time graph that will describe the cat's motion. All right, so in addition to just telling us the direction an object's traveling and how fast, a velocity versus time graph can also tell us a few other things. One thing it can tell us is an object's displacement. So a displacement means an object's change in position. So if we have a velocity time graph, but we don't have any story and we don't have a mathematical equation and we have no position versus time graph, we're still able to tell about an object's change in position. In other words, its displacement. All we would need to do is calculate its area. So I'm going to do that here. So area, if we wanted to find its displacement for the first 4 seconds, here's what you would do. You would box in the 4 seconds, like I did here, and shade in the area beneath the curve. Okay, so what I say beneath, I mean it's the shape that's trapped between the time axis, which is here. It's trapped between the time axis, the velocity axis, and the data. And then we're cutting it off by the 4 seconds. Okay, so in order to do that, you want to find the area. It looks like a rectangle. So all we need to do is base times height. And then we have a base of 4 seconds. And the height of this rectangle is 8 meters per second. So when we do this, we'll find that the seconds cancel out. And we have 4 times 8, which is 32 meters. Positive 32 meters. So what that means is that we can tell that during the 4 seconds, it traveled 32 meters, which makes sense because if you break it down piece by piece, if you travel for every 1 second, you have 8 meters. In the first second, you've gone 8. 2 seconds, you've gone 16. 3 seconds, you've gone 24. And then on the 4th second, you should have traveled 32. And that's reasonable. Now, one thing we cannot tell with a velocity time graph, unfortunately, is the initial position. There is no way to tell the initial position of the object, which is what I was getting at before with the y-intercept missing, that 20 meters that we were talking about a few slides back. That does not show up on velocity time graph because we cannot tell an object's initial position. So that's all I had to say about this, and we'll talk more in class later.